Section 4.3 is on page 336, talks about maximum and minimum. So let me start with a simple graph. Let's say we have the following function. And every time you look at a graph in any science course, you read the graph from left to right, always. If I'm taking this path, driving or walking, if I'm walking from left to right, I notice that when I get to this point, let's call that point A. When I get to this point right there, if I move to the right, I'll be going up, and if I move to the left, I'll be going up. So we're talking about 2 dimensions specifically. If I am at a point in which the only direction moving left or right is up, that makes that point a minimum. I am at the lowest possible point. If I keep on walking and I get to this point, call that B. So at this point, we'll say, well, look, if I move to the right, I'll be going down. If I move to the left, I'll be going down. Whenever you're standing at a point and moving to the right, you're going down, and moving to the left, meaning if you move in any direction, you'll be going down, we call that a maximum. And if I continue going, the same analogy, if I get to C, I notice that, wait a minute, at this point here, again, if I move to the right, I'll be going up, moving to the left, I'll be going up, then that's a minimum as well. So we have minimums at x equal A and B, and we have maximums at x equal, I messed up, A and C I meant. So minimums are right there, and a maximum right there. Now, when I get to this point, I know that's a minimum, but I can't figure out the rest of the way if I'm going to hit another minimum or not. So I continue walking, and I might hit another minimum. In this case, I did. When I hit this maximum, again, I'm not sure if I'm going to hit another maximum or not. So there could be multiple maximums and multiple minimums. Now, since these are maximum or minimums are inside of the interval, not including the endpoints, we call them local. So what's a local minimum? A local minimum is a minimum around a small interval. A local maximum is a maximum around a small interval. So you're saying there could be other maximums, you're just not sure. When we figure out there's a minimum there, we're like, okay, well, that's a local minimum around this small interval, around A. If I move to the right, I'll be going up. If I move to the left, I'll be going up. That's a minimum. When I get to this point C, at C, x equals C, around C, I notice that if I move to the left and the right, I'll be going up, and that's a definition of a local minimum or local maximum, depending what you're looking at. Now, we also have an absolute maximum, and we have an absolute minimum. Well, an absolute maximum will occur at the highest point possible over the entire interval, all of it. So when you look for the maximums, you look at the endpoint. When we say local, you can't use the endpoint because at this point, I can tell if I move to the right, I'll be going down. But if I move to the left, there's nothing on the left. And I can't use the right endpoint because, again, around the span interval, I could say if I move to the left, I'll be going down. But on the right, there's nothing there. So local, you must have an interval around the point. Endpoints don't qualify for local. Local means inside of the interval. Absolute takes on all the maximums and minimums, all of them. So all of these points plus the endpoints. And absolute maximum is simply the highest point of them all. along this path that I took, or this trail that I took, what was my highest point? In this case, my highest point was my starting point. When I started, I was at the highest possible y. And the lowest point seems to be right there. That seems to be lower y than any other y. So a local maximum could be an absolute maximum. That's not an issue. But an endpoint can never be a local maximum or minimum. Now I want to read those definitions based on what I told you. And pretty much they're saying what I just told you. Well, they state if you have a function that's defined over an interval and x is in that interval, we say you have an absolute maximum, so that's the highest of them. We have an absolute maximum on that entire interval at the point C if the y value is bigger than any other y value in there, and that's true. An absolute minimum works the other way. You say you have an absolute minimum if the y value is the lowest of all the y values on the entire interval. Local maximum, local minimum. A function f has a local maximum c if there exists an open interval containing c. When they say an open interval, they mean around c by a small margin. So if you have a maximum at c, if it looks like that, then they're saying by an open interval around c, a small interval around c, you should be at a peak, because pretty soon you could be doing the other thing, but it doesn't matter. By a small tiny interval around each of those, I can figure out if it's a local maximum or not. And a local minimum, the same idea. If I'm looking at this point D, I say this is a minimum by taking a small interval around it, very small interval. As long as I move a bit to the right and a bit to the left, I'll be going up. That's a minimum. Extremum simply means maximum, minimum. So here are the graphs. For the following exercises, determine where the local and absolute maximum happens. Some space. Well, let's see. If I walk left to right. Now, in this book, they're assuming that if you read the problem, it says maximum. Assume the graph represents the entirety of the function. So this is limit. It stops right there. That's what they're saying. So on this problem, we notice we have local minimum of, so isn't this a minimum right there, of negative 40 at x equal negative 3. We go up, that's a maximum. We have a local maximum of, what does that look like? It looks like a 10 at x equal negative 1. Now, I'm not going to get into those points, but I'm going to say that looks like a minimum. But again, this is a bit hazy. It shouldn't have been that close. But we have another local minimum of 0 at x equal to. And that's pretty much all there is. Now, when I get to the absolute, we have an absolute max. What's the highest point? It seems that's the highest point of 60 at x equal negative 4. And we have an absolute minimum. So the lowest point on this graph is right there of negative 40 at x equal negative 3. So from a graph, it's not that bad. You could eyeball it and figure it out. If I look at the next problem, we have a local max at x equal, and we have a local min at x equal. Let's see. We have a local maximum right there at negative 2. We have a local maximum at 1. We have a local minimum at negative 1. And this is a local minimum at 2. we have an absolute max and we have an absolute min. So it seems that's the highest point on the graph, and it seems in this case it happened to be the endpoints. It doesn't always have to be. Now, something to really pay attention to. This is what the next theorems talk about. Did you notice when we have a maximum, the slope of the tangent is 0, and we have a minimum, the slope of the tangent is 0? Do you notice when the function is decreasing, so here, aren't you decreasing? The slope of the tangent is negative, and when the function is increasing, the slope of the tangent is positive if you draw the tangents. If I draw the tangents here, wouldn't the slope of that be negative? So that's something we developed before, but when there's a minimum and a maximum, it seems the slope of the tangent, which is a derivative. So whenever you have a maximum or a minimum, the slope of the tangent, which is the derivative at b, it seems that's a 0. Well, the next theorem says there are critical numbers. Those are points in the interior. So C is in the interior of the domain of f of x. So let's say you have a domain from whatever, -10 to 10. Then C must be between -10 and 10 inside of it, not including -10 and not including +10. If f prime of C equals 0, or f prime of C does not exist, then that's what we call a critical number. And what's so important about a critical number? The next theorem, Fermat's theorem, says if f has a local extremum, meaning if f does have a local maximum or local minimum, and it is differentiable, then the slope of the tangent must equal 0, which means the derivative at that point must be 0. Well, algebraically, the way we're going to show this, we're going to take a derivative and set it equal to 0 to figure out what those c's are. So we find critical numbers, and we check based on those critical numbers whether we have a local maximum or local minimum, and we'll elaborate on that in a minute. Well, in pre-calculus, you learned that given a quadratic, it either opens up if a is positive, and if it opens down, if a is negative. Well, if it opens up, you have a minimum value, and if it opens down, you have a maximum value. And students end up memorizing that happens at the vertex. And you memorize that the vertex has an x-coordinate of -b/2a. Either you complete the square on this, or you simply memorize -b/2a. That gives you the x value of the vertex, and you figure out where the maximum or minimum is. Now we want to prove that using calculus. According to Fermat's theorem, since this has an extreme, a maximum or a minimum, it must occur when the derivative equals 0. What's the derivative? A, b, and c are constants. Isn't that 2ax plus b? And where does that equal 0? Subtract b from both sides and divide by 2a, and there it is. According to Fermat's theorem, that's the c. That's where f will retain its maximum or minimum. Now, we want to find the critical number. So this is what we're going to do. We're going to pretty much work those two out on every single problem. We're going to take a derivative, set it equal to 0, see where is it undefined, and from there, we're going to figure out what c is, and we're going to call c a critical number. If there is a maximum or a minimum, that's going to occur at a critical number. So the first set of problems, they want us to practice finding the critical numbers. Now we're going to do this on every problem. We're going to take a derivative, which is 12x squared minus 3. And we're going to check two things. Where does the derivative equal 0? Where does the derivative not exist? Well, a function does not exist In this case, a polynomial exists everywhere, but where does it equal 0? When 12x squared minus 3 equals 0, 12x squared equals 3, 3 over 12, which is 1/4, and if you square root both sides, you always pick a plus or minus. So we have two critical numbers, positive 1/2 and negative 1/2. If f does happen to contain a maximum or a minimum, it must happen at one of these points. How do you figure that out? That's coming your way. And what about this problem? Can't I say this is x minus 1 to the negative 1? And when I take a derivative, bring the power down, subtract 1 from the power. And y prime is negative 1 divided by x minus 1 squared. And now we're going to ask the same question. Where would y prime equal 0? Where would y prime not exist? A fraction equals 0 if the top equals 0. Negative 1 can never be 0. So the derivative can never be 0. We learned that in rational functions in the previous course. When we graphed rational functions, we figured out the y-intercept and the x-intercept. And that's how we figured them out. So that's when this happened. In case you've forgotten, where does it not exist? Since it's a fraction, when the denominator equals 0. That's when x minus 1 squared equals 0 or x equal 1. So here we have one critical number, and that is x equal 1. Here we had 2. You could have multiple depending on the function itself. Okay, I'm going to take the, you know what, let me just leave it there. I was going to squish it up there. That's okay. We don't need that much space, but how about here? If I take a derivative of this, derivative of tangent is secant squared of x, and that happens to be 1 over the cosine squared of x. So when I say where does y prime equal 0, where does y prime does not exist? So we do that in every single problem. Well, a fraction equals 0 if the top equals 0. 1 can never be 0, so this is not going to happen. Where does y prime not exist? It does not exist when the denominator equals 0. When the cosine squared of x equals 0, that's a special case. Cosine equals 0 right there and right there. So that's when x equal pi over 2 plus pi k. So pi over 2, add pi right there, or subtract pi. What's k? K would be all integers. 0, 1, 2, 3, 4, negative 1, negative 2, negative 3, dot, dot, dot. How about this problem? Here, you're responsible to know that this is really the square root of x cubed minus 3 the square root of x to the 5th. So you need to know that x has to be bigger than or equal to 0 because we're dealing with an even index radical. So here, they don't tell you anymore what's the domain. You have to list it yourself, especially when we're finding these values. So any negative value will not be accepted. Well, if you take a derivative, bring the power down, subtract 1 from the power. Bring the power down, subtract 1 from the power. 5/2 minus 1 is 3/2. Now, where does y prime equal 0? Where does y prime not exist? Well, this exists everywhere as long as x is bigger than 0. To figure out where this equals 0, I'm going to factor. I'm going to take 3/2 x to the 1/2 minus 15/2 x to the 3/2 equals 0. I'll take 3/2 x to the 1/2 out. When I take this divided by this, I'll get a 1. When I take a negative divided by a positive, that's a negative. 15/2 divided by 3/2 is a 5. And x to the 3/2 divided by x to the 1/2 is x to the 2/2, which is 1. So I get x equals 0 or x equal 1/5. In this case, I have two critical values to test, and they're both valid because they're in the domain. This problem, remember, that's really what that means. When I say take a derivative, you bring the power down, subtract 1 from the power, times the derivative of the inside. So obviously, I'm looking for this equals 0 because sine and cosine exist everywhere. So where would this equal 0? That's when twice sine of x cosine of x equals 0. That's when sine of x equals 0 or cosine of x equals 0. Well, sine of x equals 0 at 0, pi, 2 pi, when x equals 0 plus pi k. And cosine of x equals 0 at pi over 2 plus pi k. You could leave your answer like that, that's not a problem. Most likely the author will combine those answers. The author will say, look, cosine is 0 right here and right here, and sine, that's sine, and cosine is 0 right here and right here. If you look at those angles, that is really x equal 0 plus pi over 2k. Again, you don't have to combine them. That's not a problem. You could test each of those individually. You're going to get the same results anywhere. But here we have an infinite amount of critical numbers. Now we get to the actual work on this where we have to find it. Find the local maximum or absolute maximum and minimum. All right. Well, remember, derivative could find inside of the interval. The calculus could find the local. So we have, or they're asking for absolute. If they're asking for absolute, first thing we figure out what's f of negative 1. F of negative 1 is a 4. What's f of 4? F of 4 is 16, 19. So we have two values so far. Now we need to figure out in the inside of the interval if there's a value lower than that and a value greater than that. How do you do that? You take a derivative. Figure out the critical numbers. That's 2x. Set it equal to 0. That's when x equals 0. Now this is how we play the game. And we're going to do this on every problem. We list the actual critical numbers. There's the derivative. And we test the derivative. We pick a point to the left of 0. Let's say negative 1. If we put negative 1 in there, would that be positive or negative? 2 times negative 1 is negative. And we pick a point to the right of 0. So again, we put the critical numbers there. If you pick 1, if you put 1 in there, 2 times 1 is positive 1. Now remember, wherever the derivative is negative, the function is decreasing. Wherever the derivative is positive, the function is increasing. So we have a local minimum. That looks like a minimum, right? We have a local minimum at 0. So f of 0 is 3. And these are the three values I have to compare between. The highest of them will be the absolute minimum, and the lowest of them will be the absolute minimum. Based on what I found, I'm figuring that the absolute maximum of 19 at x equal 4 and an absolute minimum of 3 at x equals 0. And that's pretty much how we're gonna work these out. All right, the next problem up again, and the only reason we're doing this because they're asking for absolute maximum. What's f of negative 1? If you put a negative 1 in there, you get a negative 1 minus 1. That's negative 2 squared, that's a 4. And if you throw in a 1, you get 1 minus 1, that's 0. So far we have two values. So far this is the absolute maximum, this is the absolute minimum, unless within the interval between negative 1 and 1, we have a local maximum that's higher than this or a local minimum that's lower than this. And the only way to find that out is to take a derivative, bring the power down, subtract 1 from the power. And obviously this cannot be undefined, so we just set it equal to 0. That's when 2 x into 1 minus x into 1 minus 2x equals 0. So x equals 0, x equal 1, and x equal 1/2. We have three values to consider, and they're all valid because they're all between negative 1 and 1. We have 0, 1/2, and 1. Now, I don't need to worry about to the right of 1 because we're going to stop at 1, but to the left of 0, say at -1 for testing. If I put -1 right there, 2 times -1 is negative, 1 minus a -1 is positive, and 1 minus 2 times -1 is 1 plus 1, that's positive as well. So this will be multiplying or dividing one negative, we leave the negative. Oops. A point between 0 and 1/2, let's say 1/4. So if you put 1/4 in there, 2 times 1/4 is positive, 1 minus 1/4 is positive, and -2 times a fourth is a half. 1 minus a half is a positive. And if I pick a point between 1/2 and 1, say 3/4, again, you don't want the value, just want to know if it's plus or minus. 2 times 3/4 is positive. 1 minus 3/4 is positive. And 3/4 times -2 is -3/2. 1 minus 1.5 is negative. So if the derivative is negative, the function is decreasing. If the derivative is positive, the function is increasing, then decreasing. It seems we have a local minimum at 0. F of 0 is what? If you put a 0 in there, you get a 0. We have a local maximum at f of 1/2, right? That's a maximum. If you put 1/2 in there, you get 1/2 minus 1/4 squared. That is 1/4 squared, so that's 1/16. And 1, we already have 1 right there. So when they say find the local and absolute maximum, we have, here we didn't say, we have a local minimum at 0, 3, or x equals 0. Here, we have a local minimum, so we should say that. We have a local minimum at x equals 0, and if you plug 0 in, you get 0. And we have a local maximum at 1/2, 1/16. All right. Now, if I look at these y values, there are 4 of them. The highest of them is the absolute, and the lowest of them is the absolute. So the highest is the absolute maximum. We have absolute max at x equal -1, and that's a 4. And the lowest of these points is a 0. We have an absolute min of 0 at x equal 0 and 1. So they happen to be at 2 places, and they're equal. All right, and that's pretty much it. We get to this problem. Here, they restricted the domain for us. Otherwise, I was going to say find the domain. They're saying 1 to 9, since they gave us an interval. F of 1 is the square root. 9 minus 1 is 8. And f of 9 is 0. Well, if I take a derivative, that's 1 divided by twice the square root of 9 minus x times the derivative of 9 minus x, which is -1 by the chain rule. Where does y prime equal 0? Where does y prime not exist? These are the critical numbers. So -1 can never equal 0. This fraction can never be 0. It does not exist when the denominator equals 0. And that happens when x equal a 9. So I only have one point to worry about, which is a 9. I can't pick a point, so we're looking from 1 to 9, right? We're not going to pick anything to the right of 9 because that's not in the domain. But again, since they restricted the domain, let's just look at that. If I pick a point to the left of 9, say 1. If I put 1 in there, that will be negative divided by 9, and minus 1 is positive. Now, if the derivative is negative, the function is decreasing. If you have a function that's decreasing all the time, this is what you can conclude. You can make few conclusions out of that. One, you know the absolute maximum, since they're cutting that off on 1 and 9, and this is decreasing, the absolute maximum is for sure f of 1. So it's always decreasing. This is the highest point. And the lowest point, obviously, I don't need any work on that. It's f of 9. Because this doesn't have any local maximum. So we know this is f of 1 is radical 8. That's the absolute maximum, and that's the absolute minimum. Again, and if you have a function that's always increasing, so let's say, I'm going to erase this. Let's say you're looking at a function that's always increasing. Then the left endpoint is the absolute minimum, and the right endpoint is the absolute maximum, like exponential. you know, for example. Okay, we get to this problem. Again, they gave us a restriction. Let's see how this plays. So what we're going to do here, we're going to plug in 0. First, we're going to say, well, look, since they want the absolute maximum, absolute min, otherwise we wouldn't worry about that. F of 0 will be 0 over 1, which is 0. F of 100 will be 100 over 100 plus 1, 101. So I have two values. Now, what's the derivative? Quotient rule. Derivative of the top times the bottom minus the top times derivative of the denominator all over the denominator squared. Y prime would be 1 plus x minus x over 1 plus x squared. The derivative is 1 divided by 1 plus x squared. Well, where does y prime equal 0? Where does y prime not exist? Y prime equals 0 when the top equals 0. That can never happen. Where does it not exist? Obviously when x equal negative 1. Well, if x equal negative 1, then I have 1 point to worry about. Now, I'm not going to pick points to the left because we're looking from 0 to infinity. Pick a point to the right. 0 to 100, I'm sorry. So I'll pick any point. I could pick 0, 1, 2, 3. Let's say I pick 4 as a test point. The top is always positive. The denominator, since you're squaring it, you put a 4 in there. No matter what you put is a positive. Here's an example of a function that's always increasing. If this function is always increasing to the right of negative 1, well, wouldn't that mean at 0, it's the absolute minimum? And wouldn't that mean the right endpoint will be the absolute maximum? And we know what these values are. So the absolute maximum is 101 divided by 100 divided by 101, a number a bit smaller than 1, and the absolute minimum is 0. Next problem up. This is a square root. Domain x is bigger than 0. Again, they restricted the domain. First things first, what's f of 0? F of 0 is 0. And what's f of 4? F of 4 is square root of 4 minus square root of 4 cubed. What is that? That is 2 minus 2 to the third is 8. That's negative 6. So I have two values to compare. Up till now, negative 6 is the lowest and 0 is the highest. I need to know inside the interval what's going on, so I take a derivative. Now, y prime would be 1 divided by twice square root of x minus derivative of this, 1 divided by twice square root of x cubed times the derivative of the inside, which is 3x squared. To get a common denominator, that is twice square root of x cubed. You multiply this by square root of x squared, top and bottom. Square root of x is x if you're looking between 0 and 4. That's for sure x, not absolute value, minus 3x squared. And here we are. So now what are we going to do? We're going to figure out where does y prime equal 0 and where does y prime not exist. Well, y prime equals 0 when the top, if you take the top, factor an x out, that is 1 minus 3x equal to 0. That's when x equals 0 or x equal 1/3. And the denominator equals 0 when x equals 0. All right, so I have those points to test. 0, 1/3. Now, I don't need to worry about the left because they restricted this between 0 and 4. So this is the only interval I have to be concerned with. Well, pick a point between 0 and 1/3. Now, if you're dealing with fractions, always take half of this. Half of 1/3, that will be 1 over 6. That should be your test point. That gives you nice results. Put that in there. 1/6 is positive. If you put 1 over 6 in there, negative 3 times 1 over 6 is negative 1/2. 1 minus a half is positive. If you want a point to the right, say 1, 2, 3, 4. Put a 1 in there, that's positive. And 1 minus 3 is negative. Positive times a negative is a negative. If the derivative is negative, the function is decreasing. If it's positive, the function is increasing. We have a local max, right? That's a maximum at x equal 1/3. And what is that? What's f of 1/3? Let's see. F of 1/3 is the square root of 1/3 minus square root of 1/3 cubed. Now, Now I could clean that up a bit. I could say that is 1 over square root of 3 minus 1 over 3 radical 3. The important part is that this is smaller than this, so this is positive. But there's no way it's going to be, well, there's nothing to compare it with. I have a positive value and a negative value. Wouldn't that mean that the absolute max is the positive value? Of course, you could plug that in the calculator and figure it out. And the absolute minimum will be at absolute minimum of at x equal 1/3 and absolute minimum of -6 at x equal 4. So there, we got the absolute maximum, absolute minimum, and we got the local. By the way, I forgot to mention here, if a function is always increasing, there are no local extrema. And if it's always decreasing, there are no local extremum, meaning no local maximum, no local minimum. It must change direction for that to happen. All right. Now, they pretty much eliminated the interval. They say find the local and absolute minimum and maximum over the interval. Well, let's see how this works. What's y prime? That's 3x squared minus 12. So obviously this cannot be undefined. Where does that equal 0? You factor a 3 out, or you however you want to do it. That will be x squared minus 4 equal to 0. So 3 into x minus 2 into x plus 2 equal to 0. So we have critical numbers are -2 and 2. There's the derivative, and there's y. Pick a point to the left of -2, say -3. -3 minus 2 is negative. -3 plus 2 is positive. Negative times a positive is a negative. Pick 0. 0 minus 2 is negative, and 0 plus 2 is positive. That's also negative. And pick a point to the right of 2. If you pick a point to the right of 2, let's say 5. 5 minus 2 is positive, and 5 plus 2 is positive. So in this case, oh, I messed up. When you pick -3, -3 minus 2 is negative. -3 plus 2 is -1. That's actually a negative, not a positive. So negative times a negative is a positive. So what do we know here? If the derivative is positive, the function is increasing, decreasing, increasing. What does that mean? That means we have a bit of space. We have a local max because that's a maximum, right? A local maximum at x equal -2, and we have a local minimum at x equal 2. Now, if this function keeps on increasing, doesn't that mean infinity is going to go up to infinity and this is going to go down to -infinity? So that's pretty much it. Infinity and -infinity are always the absolute maximum minimum. You don't say that. Okay, how about this problem? What's the derivative? Well, product rule. 3x squared into 1 minus x to the 6 plus x cubed times, bring the power down, subtract 1 from the power, times the derivative of the inside. Now, where does that equal 0? You factor. You take x squared out of both of those, and you take 1 minus x to the 6. If you take this first piece divided by this, you'll have a 3 left. Oh, not to the 6, to the 5th power. You take the smaller power, right? You have a 6 and a 5, you take the least of them. So when you take this divided by this, you'll have 3 and a 1 minus x left. You see that plus? It's right there. Now when you take this divided by this, well, this cancels out. This cancels out. And 2 of those cancel out, you have 1 left. So pretty much you have a -6 times x left. So x squared into 1 minus x to the 5th, and this is 3 minus 3x minus 6x equal to 0. X squared into 1 minus x to the 5th into 3 minus 9x equal to 0.
So what are the critical numbers? The critical numbers are x equals 0, x equal 1, and x equal 1/3. Three values I have to really worry about. Let's put those on 0, 1/3, and 1. Well, this is y prime. A point to the left of, let's say, 0, -1, that's always positive, so that doesn't contribute anything. But if you put it in there, 1 minus a -1 is a positive, and if you put a -1 there, 9 times -1 is +9 plus 3, that's a positive. A point between 0 and 1/3, take half of that, 1/6. 1/6 squared is positive, that's always positive. 1 minus 1/6 is positive. If you put 1/6 in there, -9 times 1/6 is -9/6, that's -3/2. 3 minus 3/2 is positive. If I pick a point between 1/3 and 1, multiply this by 2, 2/3. Put that in there, that's positive. 1 minus 2/3 is positive. If you take 3 minus 9 times 2/3, oh, I messed up, didn't I? When you put 1/3, when you put 1/6 minus 9 times 1/6, was that correct? That's 3/2. Yeah, that's right, that's positive. No mistakes. Here, you'll say that is 3 minus 6, that's negative. And a point to the right of 1, let's say you pick 10. 10 squared is positive. 1 minus 10 to the 5th is negative. And 3 minus 90 is negative, so that's a positive. So we have a positive, a negative, and a positive. That means we have a local max at x equal 1/3. And we have a local min at x equal 1. And of course, we could figure those out. There's the equation. So x cubed into 1 minus x. So if you take 1/3 and cube it into 1 minus 1/3 to the 6, that's 1/27 times, this is 2/3 to the 6th power, whatever that is. And if you put a 1 in there, 1/3 to the 1 is 1, into 1 minus 1 to the 6, that's 0. And there it is. Okay. And if I look at the next problem, if I take a derivative, quotient rule, derivative of the top times the denominator minus the top times derivative of the denominator all over the denominator squared, y prime would be 2x squared minus 2x, if you distribute the negative n, minus x squared plus 1 over x minus 1 squared. Y prime would be x squared minus 2x plus 1 over x minus 1 squared. And if you factor that, since you're going to have to do that, x minus 1 squared over x minus 1 squared, I get y prime to be 1.
So now what are my critical numbers? Critical numbers are 1 not because of this one, because you canceled x minus 1, the domain, in my derivative. Where does y prime not exist when x equal 1? Even though you canceled it out, that's still the case. So there's y prime and there's y. You pick a point to the left of, well, no matter what you pick, isn't y prime always positive regardless? If you picked a point to the left of 1, say 0, y prime is positive, 1 is positive. If you picked y prime to be 2, y prime is positive. So we have no local minimum or max. Now I just wanted to point one thing out really quick. In the very beginning, I know probably you all didn't look at this and overlooked that. Couldn't have I said this is x minus 1 into x plus 1 divided by x minus 1? Isn't that x plus 1? Isn't that a straight line with a hole at x equal 1? And a straight line does not have a non-horizontal line does not have any local extrema. And that's pretty much it.